Continuing along, we've previously discussed functions of several variables, and we're building towards our understanding of partial derivatives. But right now we're going to talk about limits and continuity in higher dimensions. We're going to start with limits. And before we begin, let's think about what we know from Calc 1. All right, so we know some information about limits from Calc 1. So we have some x naught, and potentially there is a curve. Somewhere on that curve, we've got a point x naught, y naught, and that y value over here, y naught, that corresponds to that point, represents the limit. And basically what we know about limits is that the limit as x approaches this, we'll say x naught value, from the right of our function, we have a function here, this is my curve, C is my function. So the limit as we approach that x value from the right needs to equal the limit as x approaches that x naught value from the left of that function. And if that is true, and both the left hand and the right hand limits match, we can say that the limit exists. So that's something that's really important about limits, is that the left side and the right side limits have to match. So that limit we were just looking at was in 2 space. So now that we're in Calc 3, we're going to talk about 3 space limits. So let's draw our right hand coordinate system. Got x, got y, we have z. In this coordinate system, we might have a plane floating up here in space. We'll call this plane f of x, y. So this plane is a function of 2 variables. On this plane, there exists a point. So thinking about that point, and I think it's kind of sometimes helpful to think about drawing a cube here to help us visualize where that point exists. Maybe not a cube, but a rectangular prism. Okay. So we are looking at this point in the plane, some x naught, y naught distance located at z naught in this plane of 2 variables. So f of x, y is z, and we have this point, x naught, y naught, which is in my z plane. And what we're looking at, a limit in 2 variables, the way we're going to kind of write that or think about that, we're going to say the limit as this point, x, y, approaches some x naught, y naught point for that function z of 2 variables. And so here we have 2 variables that we need to consider. So there are some questions we might want to ask ourselves. So that first question, the first thing we might think about is there a point there? And are we approaching that point? And so by is there a point there, we're saying, is there that x naught, y naught, is that point defined on that plane? And then are we approaching that point, or can we be approaching that point? The other question then we would lead to would be how many paths? So in 2 space, we had to look at how many directions? We had to look at 2 directions, from the left and right on that curve. But in 3 space, how many different ways, how many paths approach this x naught, y naught point, right? So approach the point. And the point we're looking at is that x naught, y naught in the plane. And in how many directions inside this plane floating up here, z is a function of x, y, how many different ways could we approach that point? And so there are infinitely many curves, right? There are infinitely many curves that approach that point in the plane. X naught, y naught, z naught. All right, so that's a lot to consider. You know, before in two space, we just had to consider left and right. So we had two limits to consider. We can't consider infinitely many curves. So what is the better way to find these limits? Let's look at an example. So for our first example here, we're going to consider this function, f of xy is equal to negative xy divided by x squared plus y squared. And we want to find the limit as any point in that plane approaches the point 2, 1 for this given function. Now, the first thing we generally do when we're dealing with limits is to plug it in. So if I plug 2 and 1 in for my x and y, f of 2, 1, I have negative 2 times 1 over 2 squared plus 1 squared, and I get negative 2/5. That's my limit. So obviously that is the easiest way, but that's not always the way that it works. So let's consider this same function in a second example. All right, so I'm going to look at this same function. So for our second example, we have the same two variable function, and we want to find the limit as we're considering a point on a curve approaching 0, 0 for this function of two variables. And of course, if I try to plug 0, 0 in, I can't do that, right? And that's going to be the case that you guys have most of the time. Wouldn't be fun if we could just always plug it in and get a number. So you're not going to be able to plug it in. We can't plug it in here. We'll get an undefined value in the denominator. So if we think about considering, you know, a limit from the left and a limit from the right, we don't have a specific limit from the left or a limit from the right in this space. So in R3, we need to consider the limit along different paths. So we're going to choose different paths and think about what the limit would be in that direction. And so the idea here is when we go back to two space, the limit from the left has to match the limit from the right. So what do you think would need to occur for these limits along different paths? They would also all need to match as well. Now, obviously we can't choose every path, so we're just going to choose a few paths. So for example, one thing we can do is we can look at the limit along the x-axis. And so what does that mean? That means we would be letting y equal 0 in the function, which is going to give us this new function, f of x is negative x times 0 over x squared plus 0 squared. F of x is 0 over x squared. So in this situation, if I think about this limit as xy approaches 0, 0, if I let y be 0 for this function, that means essentially I'm doing the limit as x approaches 0, and my function became 0 over x squared, which is the limit as x approaches 0 of 0, and of course that limit is 0. All right, so now let's look at the limit For part B, we'll say the limit along the y-axis. So in that situation, we would be letting x equal 0 in our function. So this limit, xy, approaching 0, 0 for my function, well, we could think about that as just looking at the limit as y approaches 0, and my f of y, if I plug 0 in for x, would give me negative 0 times y over 0 squared plus y squared. So that's the limit of 0 over y squared, which is also 0. So this is good news, we think, because clearly we have two limits that match. So we looked at choosing these two paths, and we let, x be, or y be a constant value and x be a constant value, and what happens along that function as the y approaches 0 or x approaches 0 respectively. So let's look at a third example just to make sure. Let's check more than two because, there are infinite paths. So let's look at the limit along the y equals x path. So in order to do this, we're either going to replace all of the x's with y's or all of the y's with x's to make that new function. So that f of x, I'm going to replace all of the x, or the y's with x values. And so that ends up giving me negative x squared over x squared plus x squared, negative x squared over 2x squared, which simplifies to negative 1/2. So in this situation, along that path, the limit as xy approaches 0, 0, well, now we're just considering this a function. Instead of f of xy, it's f of xx. So this is the same as saying the limit as x approaches 0 of negative 1/2. And of course, that's going to be negative 1/2. So just to reiterate what I did there, I said I'm going to look at where y is equal to x on that path. If y is equal to x, my y's are going to turn into x's. My function turns into negative 1/2. So I'm just calculating the limit of that function, negative 1/2, which is negative 1/2. So we've checked a third path. Formerly, we got 0 and 0 for the two limits along the axes, but along the identity y equals x, my limit's negative 1/2. So what does this suggest to us? What does this make us think? Since different paths have different limits, then maybe the limit doesn't exist. So let's think about, what we may have learned here. And then we'll get into, the more serious definition and stuff in the next lesson. So we have the limit is 0 along the x-axis. We have that the limit is 0 along the y-axis, and that the limit is negative 1/2 along that line y equals x. So suggests that the limit does not exist. Okay, so we may have to try this more than 3 times to find different limits in this situation. So this is really kind of an inefficient or impractical way to solve these problems. So in the next video, we're going to look at the definition and what it really means, and then we'll solve some more examples to help us find limits of functions in two variables.